Hello friends, let me ask you a question. If you have to travel 25,000 kilometers with a speed of about 10 centimeters per year, do you know how much time will you take to cover that distance? Actually, we may move by a different speed, but this is not the speed by which the other aspects, other things around us move. Continents, for example, they move very slowly. The fastest speed that a continent can travel is 20 centimeters per year. Presently, the Indian continent is moving towards north by about 5.5 centimeters per year. This moves the continent and changes the geography of the earth from time to time. Today, we will be discussing the paleogeography and the life during the Mesozoic era. Mesozoic era extended for a relatively shorter period of time span of almost 185 million years, and it ranges from 250 million years to 65 million years, and compared to that of the Paleozoic era. That means Paleozoic was relatively bigger era than Mesozoic, and Paleozoic lasted for about 290 million years. Supercontinents were fragmented. Fragmented means broken, and there were marine regressions during Permian, increasing the land area. Mesozoic era is divided into three different periods. One is Triassic, second is Jurassic, and third is Cretaceous. You may be knowing this. Now, we will be discussing them in the consecutive manner. First in the series comes as Triassic. In 1834, a German geologist, Friedrich August von Alberti, coined the term Triassic for rocks originally found and recognized in Germany, and these formations were known as Bunter, Muschelkalk and Kuiper. Today, the rocks of Triassic age ranges from 200 to 251 million years. They are recognized on all and every continent. Most of these are sedimentary rocks consisting of dominantly shallow water carbonates of marine origin and siliciclastic red beds of non-marine origin. These rocks represent a record of sedimentation on and around the vast Pangean supercontinent. Then what is Pangaea? Pangaea actually is a large supercontinent which was made up of by joining of the all other continents. So, the earth at that time had only one continent which was formed by the coalescing of the other continents. So, it was a supercontinent and we had one vast ocean. And it narrates the event of its final union and initiation of the subsequent fragmentation also. Now, we will be discussing the paleogeography. At the onset of the Triassic, that means when the Triassic started, the world's continents were assembled into a single supercontinent. I was telling you that this single landmass was called as Pangaea. Pangaea was one single continent that existed in the Triassic. The rest of the globe comprised a single ocean, and that single ocean is called as Panthalassa. That means in Triassic, the paleogeography was that the earth had only one continent, that is Pangaea, and only one ocean, that is Panthalassa, and it was found along with a westward extending branch of the Panthalassa, and this branch was called as Tethys. Tethys was a kind of an ocean. This followed the late Paleozoic assembly of the continents when Laurentia, Asia and Gondwana collided along the Alleghenian, Variscan, Ural mountain chains. The nearly hemispheric Pangean supercontinent was encircled by subduction zones that dipped beneath the continents, while the Panthalassan and Tethyan plates carried island arcs and ocean plateaus that were destined to become accreted to the continental margins. The supercontinent drifted northwards. That means it started to move towards north and rotated clockwise throughout the Triassic. Now, let me explain this a little bit. Actually, imagine a ball, imagine any ball, and try to draw a straight line onto that ball. Whenever you will be drawing any line onto the surface of the ball, it will be curved. Remember, when the surface is not flat, the surface is curved, you cannot draw any straight line onto that curved surface. That means, whenever you observe any movement on the curved arc or a curved surface, that movement is a kind of rotation rather than being a translatory movement. So, all these continents and cratons that moved on the surface of earth, you may see that it is moving, but it is an actual rotation along some imaginary axis. The supercontinent drifted northwards, as I said, and they rotated clockwise throughout the Triassic. So, there was considerable latitudinal spread to the landmass, which was nearly symmetrical about the equator. However, no sooner had the supercontinent been assembled than significantly fragmentation began. That means, whenever the continents they became coalesced or they became joined together, then they started to fragment. Thus, the Gondwana and Laurasia began to separate in late Triassic time with the onset of rifting in the Gulf of Mexico basin. It was not until the early Jurassic through that significant marine sedimentation took place in the nascent Atlantic Ocean basin. So, this was paleogeography. Now, we will be discussing flora and fauna, and in that we will be discussing flora first. During the Permian and Triassic, there was a complex and prolonged replacement of the Paleophytic flora by the Mesophytic flora. This was the global change from pteridophyte dominated flora of the Paleozoic to the gymnosperm dominated flora that characterized much of the Mesozoic. Triassic Laurentian floras were dominated by primitive conifers, ferns, cycads. I mean, these are gymnosperms. Gymnosperm means where the seeds are not covered by the fruit. The nature has first produced seed, and then the plants they only had seed, but then after the gymnosperms came the angiosperms, in which the seed was covered, and this covering is called as fruit. So, fruit is nothing but it is the covering of the seed. And in the Mesozoic time, the seeds were uncovered. So, this is why we call as gymnosperm. Gymno means naked and sperm means the seed. So, we had the seeds without fruit in that time. So, this was dominated by the conifers, ferns, cycads, Bennettitalians and sphenopsids. Conifers were the dominant large trees, whereas the other plant types formed the understory in coastal setting. Stands of the lycopsids, Pleuromia were the dominant form in that time. Gondwana floras of the Triassic were dominated by the wide range of seed ferns, especially the genus Dicroidium. These floras were generally composed of only few, that means not more than 10 genera. Dicroidium was dominant in a variety of vegetation types, from heath or sheath to broad-leaved forest to dry woodland. Other important elements of Gondwana floras were conifers and some of the Laurentian groups of Cycadalians and Zingos. Near the end of the Triassic, the Dicroidium flora declined and was replaced by cosmopolitan conifer Bennettitalian flora. From the end of the Permian until the middle Triassic, there is a global cold discontinuity. That means in the entire world there is no early Triassic coal. Every coal is formed before this time. This has been attributed to either the extinction of the peat forming plants at the Permian Triassic boundary. Permian Triassic boundary is a greatest mass extinction in the history of Earth, where more than 95% of the life became extinct for no time to come back. And this happened something like 250 million years from now. And this particular non-availability of coal in Triassic can be also attributed to some unfavorable tectonic conditions for the coal preservation through unfavorable climatic conditions. And these and other factors may also be a reason why we do not get coal in the Triassic. Actually, to find coal, coal is usually formed by the organic matter, as you know, and organic matter is to be cooked before it forms the coal. That means whatever raw material you bring to eat is not your food. You have to cook it and then it becomes your food. So, raw material is not food, this is what you have to understand. Then the organic matter also is not coal. The organic matter has to be cooked before it forms the coal. So, in order to cook the organic matter, you have to subside it very fastly. And what the rivers which bring the organic matters do, the river has a tendency to shift in a horizontal plane on the earth's surface from one point to the other. So, if the river keeps on shifting, it will never subside, and it will, if it is not subsiding, organic matter will not be cooked. So, in order to make the organic matter being converted into coal, you have to switch off this shifting, and to switch off this shifting, you have to subside that river channel, and this happens through some fault or fracture or tectonics. So, because of this tectonics, the river channel keeps subsiding. So, when it entrenches into its own valley, the river cannot move laterally, and then it keeps entrenching, keeps subsiding, and that subsidence and subsequent deposition, it gives the mass, and therefore, the organic matter cooks and you get coal. So, the river channels have to be switched off by some tectonic activities before it forms the coal. Anyway, we will be discussing on this topic in other lectures. Now, we will be focusing onto the fauna. The fauna in the Triassic was very different and diverse, and late Paleozoic seas were dominated by the Palmatozoans, brachiopods and bryozoans, but mollusks dominated the Triassic seas. Most prominent of the Triassic mollusks were ammonoid cephalopods. Their rapid diversification during the Triassic provides a fossil record by which Triassic time has long been measured. Most Triassic ammonoids were ceratidians with relatively simple suture lines. These were descendant from only two ammonoid stocks that survived the Permian Triassic boundary crisis. The Otoceratids and the Xenodicids Triassic ammonoid genera define three broad marine paleobiogeographic provinces. One is Tethyan, second is Boreal, and the third is Notal. So, these are the three broad paleogeographic provinces, Tethyan, Boreal and Notal. Triassic nautiloid cephalopods appear to have undergone relatively very little change at the Permian Triassic boundary, but reached a great diversity in Triassic, only to suffer an extensive but not complete extinction near the end of the period. There was a major turnover in insect orders during the Permian Triassic boundary biotic crisis, followed by Triassic adaptive radiation, especially of the beetles and cockroaches. Fishes underwent significant diversification during the Triassic. This is particularly evident in the appearance of a new kind of primitive archaeopterygians, lungfishes, hydrobrontid sharks and the coelacanths. Conodonts are regarded by many workers now as primitive fish group. They were relatively unaffected by the Permian Triassic mass extinction. For them, the major biotic turnover occurred at the end of the Grisebacean, and this was followed by and explosive radiation at the start of the Olenekian. By the end of the early Triassic, stocks has dwindled and there was a paucity. Paucity means a scarcity of genera for the remainder of the period. The conodonts nevertheless continued to evolve rapidly, and their tooth-like elements now provide very useful biostratigraphical markers. After a long period stretching throughout the Paleozoic, conodonts became extinct at the end of the Triassic. Tetrapod vertebrates dominated the Triassic landscapes and underwent at least two successive evolutionary radiations and extinctions during the period. Early Triassic tetrapod faunas were very similar to those of the late Permian. Most notable is the presence of the Lystrosaurus, the broad geographic distribution of which has provided the classical evidence of the integrity of the Triassic Pangea. Lystrosaurus fossils have been found in Antarctica, South Africa, India, China and Russia. So friends, this was Triassic. Now we will be discussing about the Jurassic. The Jurassic system, Jurassic is mostly known for the dinosaurs. So this system is the second of the three systems comprising the Mesozoic era. It takes its name from the Jura mountains of the eastern France and Switzerland, where as long ago in 1795, its distinctive character was recognized, although it was not until 1829 that the Alexander Brongniart first used the term Jurassic. As far as the paleogeography of that Jurassic is concerned, the early Jurassic inherited the pole-to-pole massive supercontinent of Pangaea. The opening of the North Atlantic began the process of dismantling this huge landmass, initially with South America moving away from North America to form the marine Hispanic corridor. They later linked the previously separated East Pacific region and the West Tethyan region of the Europe. This is circumstantial evidence from the faunal migration that the passage may have been intermittently open during the lower Jurassic, which provides a migration passage for the shallow marine faunas. But it was not until the later of the mid-Jurassic that it became more open passage. During the mid-Jurassic, oceanic crust began to form in the Atlantic as rifting began to separate Europe from Greenland and North America. Rifting happens between continents exactly the same way the rifting happens between people. So, rifting is a slow process and then rifting leads to the drifting. Despite this gradual opening up, however, the general layout of the continents maintained strong east-west and north-south physical barriers to the main marine faunal migrations throughout the period, leading to the well-developed bioprovincialism that did not initially break down until the mid-Cretaceous. So, this was the paleogeography of Jurassic. Now, we will be dipping down into the flora and fauna of the Jurassic time. Jurassic floral assemblages that are typically dominated by ferns, various gymnosperms groups such as cycads, bennettitales, chaetonians, zingos and conifers. Macrofloras are also well known, however, in certain shallow marine sequences, although they are often somewhat different in composition from those of the terrestrial or fluvial lacustrine facies, including more conifers and Tylophyllum, the Sphenozemitis, Bennettititis, with fewer ferns, zingos, cycads and chaetonians. Crucially, many families of the extant ferns and conifers first appear in the fossil record in the Jurassic. Coralline rhodophytes, rhodophyte means it's a kind of an algae. So, coralline rhodophyte algae are sometimes important in Jurassic. Jurassic coral reefs and bioherms, they contribute to the bounding structure, that means to build up that coral reef and to associate the bioclastic sediments in freshwater carbonate sequences. In calcified stems and reproductive bodies, that is oogonia of the charophyte, they lend themselves to the preservation as fossils and hence They may be locally abundant and even stratigraphically useful also from the mid to the late Jurassic. Jurassic calcareous nanoflora including coccoliths are still relatively poorly known, especially in the early Jurassic, owing to the great sensitivity to the diagenesis. What is diagenesis? Diagenesis is the process that converts a sand to the sandstone. That means it is a lithification process that converts loose sediment into the hard rock. The cyst of the dinoflagellates, representing the dormant phase of the life cycle of a marine planktonic alga, are frequently abundant in Jurassic marine and quasi-marine sequences, especially those that were sediments and where the relative organic material is rich in those sediments. As such, they can be excellent stratigraphic guide fossils in borehole studies, in particular in the petroleum exploration. The calcareous or agglutinated test of the benthic foraminifera are frequently common in Jurassic and in Jurassic marine sediments. In basins and platform dominated by argillaceous sediments, these associations are often dominated by the Nodosaridae, although on some carbonate platforms, Textularina may be more significant. Lower Jurassic assemblages are typical of relatively low diversity following the end Triassic mass extinctions, but diversity increases markedly throughout the mid-Jurassic. Planktonic foraminifera like Globigerina, it first appears in the early mid-Jurassic. Jurassic radiolaria are most characteristic of relatively deep water siliceous rocks, such as cherts formed below the carbonate compensation depth. Sponges, especially the Hyalospongia, which is a siliceous sponge, can locally be very important as rock formers in some very fine-grained carbonate platform sequences bordering Tethys Ocean, including building of spectacular biohermal structures. Coral patch reefs are most typical, where suitable warm, shallow water environments are developed, mainly in the middle and upper Jurassic. Although the last spiriferid brachiopods persist into the lower Jurassic. The articulate orders, Terebratolids and Rhynchonellida, they dominate the normal marine Jurassic brachiopod faunas. Virtually all Jurassic bivalve orders survive today. Some groups, in particular Trigonida and some Pteroida, including some pectinids and well-known oyster, that is Griffia, can also have limited biostratigraphical value. Jurassic gastropods are dominated by the epifaunal forms. Epifaunal means that those organisms that live over the surface. Those that dig inside the surface are called as infaunal. So, the organisms on the seafloor are of two kinds: epifaunal, that means that those that live over the surface, and infaunal, those that dig into the surface. At the end of the Triassic, the Ammonoidea faced a massive crisis and perhaps only two genera survived into the Jurassic. The early Philoceratid, that is the Rhacophilitis and its direct descendant, the first ammonoid, that is the Siloceras. Other groups such as the Ammonitida, the Haploceratina and Perisphinctia are much more morphologically varied and thrived in the epicontinental seas. Belemnoidea, in contrast, they are never as diverse as Ammonoidea, although they can still show an analogous bioprovincial distribution with distinct boreal and Tethyan assemblages. Echinoids, including both burrowing forms, irregular, and epifaunal regular forms, are however more conspicuous in some marine deposits where seabed oxygenation was relatively good, and the former in particular can even have some local stratigraphical value. Jurassic fish faunas are characterized by dominance of the bony fishes. Marine large reptile faunas are very characteristics of the Jurassic, with dolphin-like ichthyosaurs, long-necked plesiosaurs and short-necked pliosaurus being particularly significant, the latter including the world's largest carnivore, that is the Leopleurodont. This was over 15 meters in length. 15 meters means 50 feet. So, can you imagine a 50 feet long animal and which is carnivorous. Carnivorous means those animals or organisms that eat only flesh. By the Upper Jurassic, some small dinosaurs had developed feathers. Feathers means they started to fly, and the Cambrian transition birds were well underway with the famous Archaeopteryx. So, Archaeopteryx is a kind of a flying reptile, which is a connected link between birds and the reptiles. So, this was Jurassic. Now, we will be discussing Cretaceous. The Cretaceous system or the Cretaceous period is the last major subdivision of the Mesozoic time. It was established by J. Diomedes Holloway in 1822 and was divided into upper and lower series or epochs by W. D. Conibera and William Phillips that same year. Cretaceous rocks are currently assigned to 12 stages or age level subdivisions, the combination of which represents an interval estimated to lie between 145.5 to 65.5 million years. This is the longest single system of period in the entire Phanerozoic, and the Cretaceous rocks are found on all the continents. The Cretaceous is also the oldest system or period to be entirely represented in the ocean basins. Coming to the paleogeography of the Cretaceous. Paleogeographically, the Cretaceous represents the time during which Pangaea continued to broke or fragment and the continental plates began to move into their current positions. That means the earth started to acquire its present configuration, and that process began in the Cretaceous. Prominent tectonic features of the Cretaceous time includes the rifting. Rifting means cracking of the Laurasia to form the northern and the southern embayments of the Proto-Atlantic Ocean. The joining of these embayments into a single north-south trending Atlantic Ocean basin, and the rifting of the southern supercontinent of Gondwana into South America, Antarctica, India and Australia. During the Cretaceous, the sea level stood very high, flooding the interiors of most of the continental platforms and resulting in the establishment of the marine chemical conditions that favored the deposition of the calcite. This in turn led to the widespread deposition of the subsequent preservation of the rock types and uniquely associated with the Cretaceous, that is chalk. As a result of this high sea level, the Cretaceous was characterized by warm, equable, greenhouse type climate over most of the areas, with temperatures that both exceeded and were most stable than those at the present hour. That means the Cretaceous time has more warmer days than we have now. So, it is not a case when you worry about the climate changes. Some part of the climate changes can be even natural. At that time there were no humans. So, what created global warming in Cretaceous? Even Cretaceous had more warmer days than now. That means there is a natural tendency for the climate to change, in which we are very minor factors is something we have to understand at this stage. There was very little or no ice at the Cretaceous poles, and reefs, swamps, crocodiles and even dinosaurs reached the latitudes in the vicinity, and at times even greater than minus 60 degrees. Cretaceous atmospheric composition was also different from that of today, with higher level of oxygen and carbon dioxide. The Cretaceous was a quiet time for the magnetic reversals, but also a time of a very widespread volcanism. So, this was the paleogeography of Cretaceous. Now, we will be going into the flora and the faunal assemblage. Now, we will be discussing about the flora and fauna of the Cretaceous time. The Cretaceous, it is a time that witnesses to a fundamental transformation of the terrestrial flora, with the initial diversification of the seed-bearing plants. Seed-bearing plants, angiosperms, where the seeds are covered, and this covering is called as fruit. Though angiosperms first appeared in the Jurassic, naked seed gymnosperms such as conifers, cycads and zingos dominated the earliest Cretaceous landscapes. Two of the three modern phytoplankton groups, that is the calcareous nanoplankton or coccoliths and diatoms, underwent major family level diversification during this period, with the diatoms being particularly rapid family level diversification in the lower Cretaceous. Diatoms, you may be or you may not be familiar. Diatom is something which is found abundant in your Colgate toothpaste, that is very fine silica, and which when rubs against your teeth it cleans it. So, we have the diatoms as the major source of fine silica which is used to make toothpaste, and we have very different other uses also. So, this basically started to diversify since the Cretaceous and Jurassic times. Dinoflagellate maintains their very high diversities throughout the interval, albeit with a long-term drift to slightly lower family richness values through the late Cretaceous, and this continued even to the Cenozoic, that is the Paleocene. Foraminifera responded to this change in the marine environment by the maintaining a steady diversification of the benthic forms throughout the late Cretaceous, probably a response to the enhanced carbon deposition to the seafloor by planktivorous zooplankton and nekton. Planktonic foraminifera first appeared in the Hauterivian. Like most marine protist groups, corals, marine mollusks, chiefly gastropods, cephalopods and bivalves, and marine arthropods. And these marine arthropods includes crustaceans and ostracods. They underwent a long-term family level radiations through the Cretaceous and extending into the overlying Paleocene. Corals diversified strongly throughout the interval, but declined in the abundance in the late Cretaceous, presumably because of the lower magnesium-calcium ratios. It made it more difficult to secrete their aragonetic skeletons. The Cretaceous was also a time of gigantism, because it was little warmer. So, we had giant organisms, giant animals. So, we had several surface dwelling bivalve lineages, that is the Inoceremus. Inoceremus is a kind of a shell, a small shell. You can imagine the dimension of a usual small sea shell. So, it was one very normal shell was as big as 1 meters. So, this Cretaceous time was the time when the animals, they were on their greatest of their size. The abundance of the brachiopod family fell slightly in the Barremian, but recovered quickly and was maintained throughout the late Cretaceous. Bryozoan exhibited perhaps the most striking richness change pattern, where the strong and sustained diversification throughout the entire late Cretaceous. Echinoderms appear to have had the most conservative diversification history of any major marine invertebrate clade, with the slight drift to higher late Cretaceous values being driven primarily by an asteroid or starfish radiation. So, the Cretaceous period was also a time of the diversification of the starfishes. Though dinosaurs understandably get most of the attention when it comes to the Cretaceous terrestrial vertebrate faunas, but it is also important to note that essentially all modern terrestrial vertebrate groups had representatives in the Cretaceous, like salamanders, frogs, lizards, snakes, turtles or tortoises, crocodiles, birds and mammals. They are all shared the Cretaceous landscapes along with the non-avian dinosaurs or non-dinosaurian archosaurs, that is, for example, crocodile and Camposaurus and the Pterosaurus. So, we have discussed about the life and the paleogeography of the Mesozoic in 3 different and distinct sectors: the Triassic, Jurassic and Cretaceous. So, we'll be discussing about the other the geological periods, paleogeography and their life in the coming lectures to come. Hope you have enjoyed and understood this lecture. Till then, thank you very much.